Okay, so let's talk about correlation. Okay, so maybe a good way to start this is to go back and take a look at some of the exercises we have on Blackboard. Okay, and I'm going to go into that session. Okay, here we go. Okay, so I start off with kind of a little bit of a tongue-in-cheek kind of exercise, and that involves this kind of old saw in New York City that goes around that says that there's a correlation between the pizza cost of pizza and the subway fare. Okay, and I'm going to open that up in SPSS. We're going to use that as a starting point. Okay, so what this data set has when it finally opens up is it's going to have for different years what the cost of a slice of pizza was and what the cost of the subway fare was at that same time. And it covers about 6 or 7 different data points, 6 or 7 different years. But you can tell that the variables that we're working with, the price of pizza, the price of the subway fare, are both numerical variables. And up until now, we haven't really had a situation where we had to see if there was an association between two numerical variables. When we were looking at the t-test, for instance, that checked that you had two variables. You had a categorical variable such as male and female, and you had a numerical variable such as a height, and you could compare the mean male height to the mean female height, see if the means are the same or if the means are different for those two populations. We went to analysis of variance, where we were working with a categorical variable and numerical variable. Again, the difference is that the categorical variable had more than two values. For instance, it could be ethnicity. So you could have maybe 6 or 7 different ethnicities represented, and maybe we're comparing heights again is the numerical variable, and we would want to compare the mean of ethnicity one to the mean of ethnicity two to the mean of ethnicity three to the mean of so on and so forth for as many as we have, and in that case t-tests wouldn't really be appropriate because you'd have to apply it over and over and over again in all sorts of different combinations, ethnicity one versus two, one versus three, one versus four, and so on and so forth. So that would multiply your error and just wind up not working out very well. So analysis of variance is a technique for comparing means when you have more than two groups that you want to compare the means of. Very similar to t-tests. In fact, if you do analysis of variance for a categorical variable that has only two values, you'll get exactly the same result, the same p-value that you would get if you had run a t-test on that as well. Okay, even though the calculation takes a different course, it works a little bit. The final result comes exactly the same. You can give that a try one of these days if you're ambitious. So, and then we got into situations where he said to himself, well, how about when we have two categorical variables? For instance, diabetes. Let's see, intravenous drug use and HIV status. For instance, I think I have a database for that right here. Um, uh, is HIV status associated with intravenous drug use? Say we're naive. Let's say we're back in the 80s and we're evaluating this for the first time. Intravenous drug use is a categorical variable, would be yes, the subject did use injected drugs, or didn't use injected drugs. And HIV status is also a categorical variable. HIV status positive or HIV status negative, right? It's only two values that you could have there. It happens in this case that our variables are dichotomous, only two values, right? So it's easy to build a table that would describe the relative likelihood that, or if we had a number of subjects we chose at random, how those would be distributed between a 2 by 2 table. In the rows, you might have the exposure, which is drug use, right? Yes and no. And in the columns, we would have HIV status, positive and negative, right? So we would use that to evaluate whether or not there's an association between HIV use and intravenous drug use. Maybe we'll still get to that today, but there's a kind of a corollary to that, which is odds ratio and relative risk, which is kind of tied into that same table, that same 2 by 2, what we call crosstab or contingency table. So now we've gotten to the point now where the only thing left really is what do we do when we wind up in a situation where we have two numerical variables and we want to look for an association. Okay, so for instance, we might be interested if there's an association between numerical variable cost of pizza and the numerical variable the cost of subway fare over a period of time. So I'm not sure why I didn't get SPSS didn't open, but let me give it a try again. I think I'm going to have to save it from here first. We drop it on the desktop. Oh, it's already out there. Okay, well, let me minimize this and get to it. Maybe it's just waiting for me to get that window out of the way. Okay. Oh, I only have a very limited amount of time left on my SPSS installation. I'm going to have to renew it pretty soon. Okay, so, nope, I can't close this. I'm going to open data. And let me go to the desktop. My desktop, and this is what I'm looking for. Okay, so let's take a look at this. I have a numerical variable. I have a numerical variable or nominal variable, the year, right? We have the cost of pizza and the cost of a subway fare. I'm going to look at it in data view. So here are my two numerical variables. Actually, they really look almost the same, don't they? They really correlate quite closely. Normally, won't see this close a correlation between these two things. In fact, many people in New York, I don't know if you're a native New Yorker, but many people in New York would claim that they conspire to be exactly the same every year. So how would I see if these are associated? The first thing I would do is I would say to myself, let me get a look at this graphically, see if there's an association graphically. So I'm going to say I want to graph this. I like to use legacy dialogues. I just want a simple scatter dot. Now in a scatter dot, what you're going to wind up doing is assigning a dot that represents the x-axis and the y-axis. For these two variables would be the x-axis and the y-axis. So you would be plotting a dot for each value, each pair of values. So I'm going to go ahead and plot that. And we're going to want to plot the cost of a slice of pizza and the subway fare and the x and the y-axis. Now, notice that I didn't really care which one I put in the x-axis, which one I put in the y-axis. Because when we're dealing with correlation, we're not assuming causality. We're only looking for an association between two variables. The one that you probably heard me talking about in the recorded lecture was the idea that the number of firemen that go to a fire is associated with the amount of damage and dollar value that the fire does. And obviously, we know that the firemen don't cause the damage. Bigger fire, you have more firemen. So there's it's not causality necessarily, but there is an association between the two. More firemen there are, more damage is likely to have occurred, even though they don't cause it. So I'm going to go ahead and plot this graph. And our output window opens up. And indeed, if we look at this graph, oops, let me try and peg this a little bit. If we look at this graph, we can see that these are the various values for the first year, second year, so on and so forth. This one's a little bit out of sync with the others and so on, this one here. Okay, so I can actually double click on this and I can ask it to assign a line to this, which is a best fit line. Okay, and let's talk about what I mean by best fit. It has created a line a straight line, which is the best fit for all of these different values in terms of trying to fit a straight line to where all these dots are. And what it's trying to do is it's taking a look at the distance between this line and each value, the ones above it and the ones that are below it. And it's choosing a straight line that takes the square of these distances, the square of the distance between the value that you would have predicted with the line and what the actual value was, takes the square of them and tries to balance them below and above the line. Okay, uh, 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 so that this line actually represents that relationship between the cost of a slice of pizza and Subway fare. Okay. The other thing that we're interested in is the magnitude of these differences. The magnitude of these differences produces a value called the Pearson's R correlation. That's a value that's between -1 and +1. 0 means that there's no correlation at all. There's no association between the two of these. The dots would be just randomly scattered around. So there's no relationship between what's in the x-axis and what's in the y-axis. If we have a +1 correlation, that means that we would have a straight line that perfectly fits all the points. We're close here, but we're not really exactly at a +1. Okay, and if this line was sloped downwards and it hit every data point head on, it didn't miss any, that would be a correlation of -1. Negative because it's the as one value goes up, the other goes down, but it's still a perfect correlation. One is perfectly predictable from the other. So if I want to actually calculate the Pearson's correlation, I can use SPSS. Analyze in the time we have now. I'm not going to go over too much of how it's exactly calculated, but we can use SPSS to calculate it. I can say analyze, correlate, bivariate because of course we're dealing with two variables, binomial variables, bivariable. Okay, and I'm going to move in notice we can't click the OK sign over here. I'm going to move in the first variable, which is cost of a slice of pizza. Then I'm going to move in the second variable, which is the Subway fare. I'm sorry, when I say two variables, not binomial, but two variables. Okay, they're numerical variables, so they actually represent numbers, but there happens to be two variables. So I'm going to move in the cost of a slice of pizza and cost of Subway fare. Now suddenly, now that we have two variables listed here, we can go ahead and say, okay, two numerical variables or scalar variables, as SPSS calls them. I can go ahead and do this analysis, and there's a series of different kinds of evaluations correlation I could use, but for the most part, we're going to be sticking with Pearson's correlation. So I'm going to click OK, and it's going to do that calculation for us. And if we look here at our output table, the Pearson's correlation that we have is 0.988. Remember what I said about a perfect correlation would be 1. So this is very close to a perfect correlation. This is a very strong correlation. Now, is this due to chance or is it statistically significant? Well, if I look here at the significance, it's 0.000. The probability that I would be wrong if I said that there's a correlation between these two values is less than 5%. So I feel comfortable that I can say that that's true. So what would be? Let's imagine what might be a functional null and alternative hypothesis for Pearson's R or Pearson's correlation. And I'm thinking probably our best bet would be the null hypothesis is that there's no association between the two of these, and the alternative hypothesis is that there is an association between the two of these. Okay, so if my p-value is less than 0.05, I can reject my null hypothesis and accept my alternative hypothesis that there is an association between the price of pizza and the price of Subway fare, with less than 5% chance of being wrong for doing it, causing an alpha error. Okay, so this is pretty interesting. It does it twice, it does a comparison twice: pizza versus Subway fare and Subway fare versus pizza. SPS tends to do these all permutations of any calculation anyway. So now that I've done that, I feel that there's a correlation. Maybe I know that maybe I suspect that there's some causality here. Now I'm going to close this because I don't think this is a very good one to really argue causality. So what I'm going to do instead is I'm going to see if I can't find one that, let's see if I got the one with HIV. Let's see. I'm going to open this one. See what we have here. I think this is my categorical. This is all categorical. Let's see. No, HIV would be the same thing. Let me open, let's see. Let me open our North Carolina Burt's data set. I know that's a safe one. We've got a lot of variables in that one, especially a lot of numerical variables. And we'll actually do a particular calculation there, a sample calculation there. One keeps wanting me. I guess it wants me to spend the money. Okay. All right, so let's take a look, see what numerical variables we have here. Well, the mother's age is a numerical variable, the weeks of gestation, even though it's misidentified there, and I need to correct it. Mother's age, weeks of gestation is a scalar variable. Let's see what else we have. Race of the mother, the amount of weight gain during the pregnancy is a scalar variable. The weight of the baby at birth in ounces or in grams is a numerical variable. So let's see if there is an association between the weeks of gestation and the length of the pregnancy and the baby's birth weight. Okay, I think that would probably be very likely, right? So let's test that hypothesis. So our null hypothesis is that there's no association between the length of pregnancy and the weight of the baby at birth, and our alternative hypothesis is that there is an association. So the first thing I might be interested in doing is looking at this graphically to see if it appears to me that there is an association between these two. I'm going to go to legacy dialog, scatter dot, and I'm going to say, let's take a look for an association between the completed weeks of gestation and the amount of weight that the baby gained, the weight of the baby at birth. Okay, and I'm going to click OK. Whoops, let's see if it works out. Okay, here we go. Well, look, does that? I'm going to ask you a question. Does that look to you like there's an association? What do you think, Lily? Yeah, I think so too, right? I'm going to double click on this to bring the window editor up, and I'm going to make it create a line there. We'll take a look at it. Okay, good. I see that line it's created to balance both of these. Funky thing going on here. A lot of these are down low. A lot of these are up high. There's some things that are making me a little uncomfortable about this, but we're going to go ahead and move ahead also, right? So notice that down here you have very premature infants down there. So we're going to take a look at this anyway. Right? So they might be outliers and so on and so forth. You can see it really kind of like messes up our line a little bit because these are all below the line. These are scattered above and below the line. So we would rather see them randomly distributed around this line that we've done. Didn't happen this time, but let's see what we can get from this. Okay, good. So let's take a look at this from the perspective of Pearson's correlation. Let's say analyze. I'm going to say correlate. I'm going to say bivariate, the two variables, the weeks of gestation and the weight of the child, completed weeks, and the weight of the child. And I'm going to go ahead and do our analysis, our Pearson's analysis. Okay, so what do we have here? Well, we don't have as strong an association as our pizza and our Subway's fare, did we? That was an unusually strong association. But look, 0.583. It does seem like there is a pretty strong association, right? This is closer to 1 than it is to 0. Now, the question now is, it seems like a fairly strong association, which we would kind of expect, right? That's certainly not surprising to us. right? But, there's a lot of variability there. Can I be sure that this is not due to chance? How sure can I be that this is not due to chance? Well, here I have my significance, my probability that I would be wrong if I reject my null hypothesis, which is less than 0.05. So I'm at least 95% certain. I have at least, I feel that there's well less than 5% chance I would be wrong if I were to say that there is an association between the weight of weeks of gestation and the weight of the child at birth. I feel pretty good that I can say that reject the hypothesis that there's no association and accept that there is an association. That's how I feel pretty good about that. Okay, and this is the strength of the association. That suggests there's a lot of variability, that sometimes you can have a normal gestation and a smaller baby and a bigger baby and a shorter gestation and a bigger baby. That happens, right? So that's why maybe this isn't closer to one, but it's still pretty strong anyway from the perspective of most correlations you might try and calculate. Okay, now I'm going to ask you, is it a positive correlation or a negative correlation? Positive, right? Because as the weeks of gestation goes up, the weight of the mother goes up, the weight of the infant child goes up, and the line is sloping upwards from left to right as you go up the x-axis, right? Had it been the opposite, we would have called it a negative correlation, right? Still a correlation, but a negative correlation. Okay, so now let's take the next step. The next step is to quantify this in terms of causality. In other words, most of the time when you're doing these kinds of studies, you're investigating causes. You want to know if this has an influence on that, and if you make an intervention, if you can make things better, right? So we want to know how predictable is this association between these two things, and that's where regression comes in. You can Google the word regression and look, where the origin of the word regression, and it has to do with a study that was done that involved heights of children for tall and short parents and so on and so forth, and it's based on something called regression to the mean. We're not worried about that. We're really using the tools that came out of that study so I wouldn't worry too much about the actual meaning of the word specifically, but the tool that we get from it is this idea that we can have we can see we can quantify the association between these two variables, and we can use one to predict the other. Okay, in order to do that, we have to decide which one causes the other one. Which one is the dependent variable and which one is the independent variable. The independent variable is the one that affects the value of the dependent variable. So the independent variable is the causer and the independent variable is the result. So in this case, the weeks of gestation would be the independent variable, and it would determine the weight of the baby, right? So it would make sense the other way around, right? The weight of the baby would determine how many weeks that it would be carried. It makes more sense to look at it the other way around. So let's give this a try. I'm going to go to analyze. I'm going to go past correlation to regression. Okay. Now, the type of regression that we're working on here is linear regression. We're assuming that the association between these two values is represented by a straight line, a linear relationship. So I'm going to click linear. And now I have to define, I can't just throw either one in. I have to define which is the independent, which is the dependent. So we decided that the weeks of gestation is the independent variable, and the weight of the child in ounces is the dependent variable. Okay, so I'm going to go ahead and I'm going to calculate this. For right now, I'm not going to worry about this stuff. So I'm just going to go ahead and calculate our correlation and our regression. So I'm going to click OK. Okay, and let's see what we wind up with. Well, first, I wind up with model summary. Well, R is our Pearson's correlation. And you might remember that's the same number that we got before. That's literally the number that we got before. Okay, and we calculate, the SPSS calculated also a value called R squared. I won't worry, right now I won't worry about adjusted R for the moment, but R squared, right? So R squared is 0.34. It's literally this value for R squared. It has a special meaning to us. I'll get back to it in a minute and discuss what it actually means to us and why SPSS is presenting this to it, why this is important, an important number to us. But it actually calculates the probability of this result being due to chance. And as it happens, our significances are very low, less than 5%. Okay, so SPSS then gives us a box called coefficients, where we feel that this association is statistically significant, less than 5% chance that it's less than 5% chance that it's not real, that we would have rejected the null hypothesis incorrectly, right? So let's see what we have here down here as a result of this calculation. SPSS provides us with coefficients that represent the line that is the best fit, that straight line, which is the best fit line for the association between these two variables, the weeks of gestation and the correlation. Okay, so that these numbers represent that straight line. Well, how do they represent that straight line? Well, let me open up a little thing I can write on. I'm going to have to write with my mouse here, so it's not going to be so elegant. I don't have my my graphics tablet hooked up. So let's see our X and our Y axes. This is weeks of gestation, and this is the weight. I'll put a pound sign there for weight. It's ounces, actually, right? The weight of the infant. And our line looks something like this. You will remember what it looked like with all those scattered dots and so on and so forth. Well, a straight line is represented by the formula y is equal to mx plus b. There's a few ways that you can write this out. I think in most statistical textbooks, instead you'll see y is equal to, I'm going to go out on a limb here and say ax b plus b plus ax or something like that, right? Instead, but the idea is the same, right? What does the m stand for? What does the number from dx stand for? You remember that from your algebra days? That's the slope, exactly right. That's the slope of the line, right? The difference between the value for a change in x, a change in y over the change in x, right? At any point in the y. It's always the same, right? Because since it's a straight line, slope's always going to be the same, right? So this is sloping, it's a positive slope, it's a positive number, as we saw before. It's a positive association. Okay, and you remember what b was? Remember what b represents? The y-intercept, exactly. Well, you should be teaching this course, right? The y-intercept. In fact, if you look, if you plug in the value 0 for x, this drops out. 0 is the point where you cross the x-axis, right? So where you cross the y-axis. So the value 0 for x would just represent y is equal to b. So if b is over here, right? That's what will be equal. So if you know b and you know m, you can draw this line. You know this line. So if you know this, the point where you know it passes through this point, and you know its slope, maybe it slopes that way, maybe it slopes that way. If you know its slope, then you can define that line. Those two values define that line. So what are those two values for our analysis? This number, completed weeks of gestation, represents the slope of this line. Okay, 4.8. I'm going to call it 4.8 to make it a little simpler. Okay, I'll draw this again. Let me make this a little smaller. Okay. Actually, I still can't see it. Oh, that didn't help at all. Okay, I think I can do it now. Okay, so let's see. So the slope that I'm looking for here, y is equal to, okay, the slope, which is 4.8, right, positive 4.8, right, equals mx plus b, and b is minus 70. I'm going to round it off for our purpose. Minus 70. Okay, that tells us that the line crosses the x-axis all the way down there, right? Keep in mind that you're not going to have a baby that weighs 0 ounce. You're not going to have 0 weeks of gestation, right? So a lot of these values, especially the intercept, often doesn't mean anything. It's just a way to pin the value of the y-intercept and complete this formula. So really, what this is 4.8x times x. Really, what this formula represents, it really represents that the weight of the infant, right? Weight of the infant in ounces, weight of infant. It's hard to do. Infant in ounces is equal to 4.8 times x, which is the weeks of gestation, weeks of gestation minus 70. So this is a relationship that we have. So if you're a obstetrician, if you're doing obstetric research, excuse me, and you want to study the impact of an extra week or 2 weeks or 3 weeks of gestation on the weight of a child, the weight of an infant, how it might impact it. Well, this formula might be important to you, right? So you might be able to say, well, what would the weight of the infant be if the pregnancy went 28 weeks? How would we calculate that? We just say the weight of the infant is equal to 4.8 times, what did I say, 28, I think it said, 28 weeks minus 70. I'm going to get a calculator out and actually calculate this. So this formula would predict that the weight of an infant would be, see, 4.8 times 28 is equal to 134.4 minus 70 would be equal to 64 ounces. Okay, at that 28 weeks approximately, right? I rounded a lot of stuff off here as I was doing this. Well, that's interesting. Well, what about at 32 weeks? Well, at 32 weeks, it would be 4.8 times 32 minus 70 is equal to 83 ounces. So we have something that'll help us predict what the value of this other variable is, the weight of the infant, based on the weeks of gestation. Well, how good a predictor is that really? Let's go back to our table over here. Remember we had that value r squared? Well, the reason why that's important to us is, as it turns out, this value r squared, that value r squared represents the amount of variability in the weight of the infant in our result that's determined by our independent variable, by our weeks of gestation. So 34% of the variability in the weight of an infant is due to the number of weeks of gestation. Well, what does that tell you? That tells you that that's a pretty good portion of the variability, but it also tells you that 66% of it is due to other things as well. Could be the age of the mother, could be nutrition, could be genetic, it could be so on and so forth. It could be many different variables. In fact, we can build formulas like this where we examine more than one variable at the same time. And that's basically what multiple regression is, where you would get a formula where you have AX1, BX2, and so on and so forth, where you would account for A would be just the weeks of gestation, B would be age of the mother, and so on and so forth. And maybe by combining those, you could get a better resolution where you get a formula that did better than 34% because you had more than one variable. present. For the moment, let's just talk about this simple linear regression that we have here. Okay, so I just did something interesting here, didn't I? I took the formula and I said to myself, well, what would I expect to be the weight of an infant if I had 28 weeks of gestation? How about 32 weeks of gestation, and so on and so forth? Well, in fact, SPSS will help us with that. So I'm going to go up here, analyze. I'm going to go up to, let's see, regression. I'm going to go to, oh, we have a bunch of other people online now too. I didn't realize you guys were here. Okay, let's go to, where was it? Regression, linear. Okay, and again, I have my values, my independent variable and my dependent variable already selected. I'm going to go to this button called Save, right? We haven't used that much before. I'm going to click on Save. Save will permit me to actually have it record the predicted values, which is the weeks of gestation, and the residual values. And I'll talk about, we're going to take a look at what the residual values in a moment. Okay? So I'm going to ask SPS to calculate predicted values and residual values. I'm going to click out continue, and we're going to see what those are in a second, as soon as this operation completes. Okay, so it went through all of our calculations again, got the same thing, 34%, so on and so forth. Then we get some residual statistics and so on. Well, really, the interest in the residual statistics is not so, it's in the output table, but really even more interesting is the data table, okay, the data view. I'm going to go back here and notice that, let me go to data view. Notice that SPSS has added two values, two variables to all the other variables we had before. This is predicted and residual, so two things that we checked off there. Well, what is this? This is if we applied the formula to subject number one. Let's see what subject number one was. Subject number one was 40 weeks of gestation, and the weight gained was, the weight of the infant was 111 ounces. Okay, well, based on 40 weeks, our formula would have predicted that the weight would have been 123 ounces. So it was short by 12. Residuals is the error. That's the difference between what our formula predicts and what our actual infant, if we had an infant, we had an actual value for that infant, what it would be, and so on and so forth. And you can see all these different residuals. These residuals should be randomly, random throughout this, because if they're not random, it would suggest that there's some systematic error going on here, something that we're not accounting for, that systematically is confounding this data. So this is our predicted values and our residual values. Okay, so you have any questions? Are there any questions on that? I'm gonna be posting an extra video next week, as I said before, on logistic regression. Okay, logistic regression is, for instance, when we have a categorical variable, which you would normally express as a proportion, right? A probability or a proportion. For instance, if we want to know what the prevalence of diabetes is in the population, well, that prevalence might be maybe it's 10%, maybe it's 12%, so on and so forth. Well, it would be interesting if we could have a formula that would help us predict what the probability is that any individual in a population has diabetes based on other factors, numerical factors, categorical factors in that population. Okay, so, but I'll post something on that next week. So, you guys okay? Is there a question on that? I want to back up and go over a little bit of categorical analysis of variance, and on Chi-square, because I know we had some. Yeah, you guys are working on a test. I don't want to give anything away, but I want to maybe go through a quick example of it. Okay, so I'm going to move on to that. Did this help, by the way? Did this kind of like, very fast introduction to this? Oh, good. Okay, good. I'm glad. I'm glad. Okay, so let's talk about chi-square. Okay, I'm going to take this example here. Okay, in this example, we have a situation we randomly sampled. I guess this was from a hospital population or a cardiac ward or something like that. We randomly sampled people, different subjects, and we asked these different subjects, we reported for these different subjects their smoking status. Let's see if I can't get it from the variable view. One represented they smoked, and two represented they didn't smoke. Whether or not they had heart disease, specifically aortic stenosis, yes or no, and what their gender was, male and female. Okay, so I'm going to summarize all this data. You could do this manually, right, by drawing a crosstabs table. I'm going to see if there's an association between smoking status and heart disease, aortic stenosis, in this randomly selected population. I'm going to say analyze. Okay, now this is interesting. Now, I'm not comparing means. I'm not doing a correlation numerical variables. Comparing means would mean I have to have a numerical variable. I don't. These are both yes and no's. They're categorical variables. So what do I have? Well, let's go back to descriptive statistics. If I go to descriptive statistics and go down to crosstabs, I know crosstabs will at least allow me to build a table. So I'm going to click crosstabs. So in crosstabs, I can build my table with rows and columns. I usually like to put the exposure in the rows and the outcome in the columns. So in this case, I'm thinking the exposure is most likely to be smoking, and the outcome is heart disease, let's say, for instance. Okay, so I'm going to click into statistics, and I'm not going to click anything. I'm not going to do anything there. I'm just going to click into cells instead and say, show me the observed values. Summarize all of these values for me. So I'm going to click continue and click OK. So with just observed values selected, let's see what SPSS gives me. Well, SPSS summarizes these results into a table. I have 94 people who smoked, and I have 121 people who did not smoke. And out of the 94 people who smoked, 54 of them had signs of heart disease, and among the people that didn't smoke, 44 of them had signs of heart disease. Oh, okay, so what am I trying to? What might I be wanting to show here? I might be wanting to show that there's an association between smoking status and stenosis, or that there's no association between the two of them. So what would be my null hypothesis here? My null hypothesis would be starting out with that there is nothing, that there is no association between these two categorical variables. And my alternative hypothesis would be that there is an association between these two. So very interesting. So now what can I do with this? Okay, well, first of all, I'm going to get Excel up so that I can show you how this is done a little bit easier. Okay, let me zoom this up so it makes some sense. Okay, so I'm gonna just build this here. 54, 40, total is 94. Okay, and 44, and 77, and 121. Okay, so, and this is disease plus and disease minus. Got the disease, don't have it. This is the exposure, whoops, plus and exposure minus, not smoker and not smoker. Okay, I'm going to make it a little bit more general for what we're doing. Okay, let me make these. I'll tell you what, the whole column here. Make them all kind of line up a little bit. Okay, let's get them like that. Okay, good. I'm in pretty good shape now. Okay, I'm gonna draw a box around this, make it a little easier to see. I hid the box. That's okay. We'll just use it this way. Okay, so now, what's the probability that you would have stenosis, have the disease, if you're a smoker in this population? Well, that is going to be equal to 54 out of 94, right? Total number of people is 94, 54 of them have the disease. So the rate that they have the disease is 57%. Well, what's the rate at which people who don't smoke have the disease? It's equal to 44 in this population. Remember, it's an unusual population, divided by 121. 57 is the risk of having the disease for that group. 57% is the risk that you would have that disease. 36% is the risk that people that weren't exposed have the disease, right? So, look, it looks interesting. It looks like it's riskier to be a smoker than to not be a smoker as far as stenosis is concerned. So, I'm going to ask you now. I'm going to take something called relative risk, and I'm going to say it's equal to the risk for this group divided by the risk for this group. I'm going to ask you, if there was no difference between smoking and not smoking in terms of this disease, what would you expect that ratio to be? Somebody let me know. 1, right? Specifically, you expect the risk to be the same. That's going to be 1. Well, in this case, it's actually 1.6. It seems like it's 1.6 times as risky to be a smoker in this population than to be a non-smoker in this population. Well, this idea of relative risk is so nice that I'm gonna complicate it. But before I complicate it, I want to ask you one other thing. We would have expected the relative risk to be equal to 1. We calculated it to be equal to 1.57. But that's only in our sample. We don't know what it is really in the population. What do I need to calculate in order to really compare it to 1? To really know whether the relative risk for the entire population is different than 1. What would I need to calculate for this relative risk? Odds ratio is coming up. Odds ratio is right, but what do I need? What do I need to prove with less than 5% chance of being wrong that there really is a difference between this and 1, between this relative risk and 1? I need to know the 95% confidence interval for the relative risk. And if the 95% confidence interval, I like critical value, but in this case it's going to be confidence interval, right? If the 95% confidence interval is 1.1 to 2.3, that means I'm not, even though I calculated it to be this number, I'm 95% sure that the true population mean is between 1.1 and 2.3. So I'm 95% sure that it's more than 1, right? So my null hypothesis, the relative risk for smoking versus non-smokers is equal to 1. My alternative hypothesis is my relative risk is not equal to 1. So if this is the case, I can reject my null hypothesis. If this turned out to be 0.9 to 2.3, right? Well, then I couldn't say with 95% certainty that it's not 1. So I fail to reject my null hypothesis. That the null hypothesis being that the relative risk is equal to 1. Okay, so now you got ahead of me there. You got to that odds ratio thing, right? So let's do that. Let's do the odds ratio now. I'm gonna clear this. So I got a little bit of space to work with. Okay, clear it all. Okay, so how do we do the odds ratio now? Well, the odds is a funky thing that a little bit funkier. If you go to horse races, when you see the odds on a horse, and the horse is 5 to 1, that doesn't mean it's 5 times as likely to win. It's not 5 times as likely to win, right, or lose. What it means is if the horse were to run 6 times, it would lose 5 times and win once. They do it that way because it's a lot easier to calculate the payoffs. Like you bet $1, you get 5 back, that kind of thing, right? So 5 to 1 means that if the horse ran 6 times, 5 times it would lose, 1 time it would win. If the horse is 3 to 2, right? Well, what that says, if the horse ran 5 times, that's probably a favorite. That horse had a strong favorite. If the horse runs 5 times, you would expect it to win 2 out of 5 times, right? So that's the way odds works. In this case, the odds is not going to be 54 over 94. That's the risk, right? The odds are going to be equal to the odds that the probability that somebody has the disease divided by not having the disease for that group. So the odds here are 1.35. And the odds for people who are not exposed, that don't smoke, are equal to 44 over 77. Okay, so those are the odds. So now we can do the same thing. We can calculate an odds ratio. And what would we expect the odds ratio to be if there was no difference between smoking and non-smoking? Same as before, right? It's going to be equal to 1. That's our null hypothesis. Is the odds ratio equal to 1? And in this case, the odds ratio is equal to this divided by this, which is a bit more, but it's the same kind of outcome that we would have expected from our relative risk. Our relative risk also showed an increase in risk, because of smoking, right? And again, we would want to know a 95% confidence interval for the odds ratio to make sure that we can say with less than 5% chance of being wrong that it's different than 1. So how do we do this with SPSS? Well, we're not quite done yet. Okay, there's another way we could evaluate this table that compares what the output would be if there is an association versus what if there is no association. And that is, I'm going to insert a couple of rows here. And the way that works is that this table is called the observed values, right? This is actually what we observed when we took a sample. These numbers, these all represent people that we observed. Now, I'm going to make another table here, expected values. What would I expect if I sampled, what is this, the sum of this? What would I expect if I sampled 215 people from this population, 94 smokers, 21 non-smokers? What would I expect the outcome to be if there's no association? Okay, well, let's see how many people have the disease in here. That's equal to the number of people that have the disease is 54 and 44 is 98 people out of 215, right? Whether they smoke or not, the overall total is 98 out of 215. So what is that? That's equal to 98 divided by 215. That's the number of people who have disease over the total number of people that we sampled. What do we call that? The percentage of people in the population that have a disease. What do we call that? Call that the prevalence, right? That's the prevalence of the disease. Great, thank you. Right, so that's the prevalence. So if we make up a new table where there's 94 people that smoke and 121 people that don't smoke, how many people that smoked would we expect to have this disease? Well, it's going to be equal to 94 times the percentage of the population that has the disease overall, right? It's going to be we expect to get 42 people. Well, how about the 121 that don't smoke? Well, we would expect that 121 to be getting the disease at the same rate as everybody else, 45%. So we would expect, whoops, I didn't put an equal sign in there, equals times this value, the prevalence. We would expect a 55 in there. So if I had to do the rest of this calculation, this would be 94 minus this, so that would add up, and this would be equal to 121 minus this to complete my table. Notice these are not round numbers anymore. So if there was no association, I would expect to have 43 people here, 55 people here, 51 people here, 65 people here. But what did I really get? Well, among the people that smoked, I got more than I would have expected if there was no association. Among the people that didn't smoke, right? I still got more, right? Oh yeah, I got less, rather. I got less than I would have expected. I got more here and less here than I would have expected. Oh, it sounds like there's something going on here. That this is causing something. Now, we want to create we're going to create ourselves a new statistic. We're going to call that chi-square. Okay, chi-square is a big, X, Greek letter chi, it's a big, kind of a big X. we want to create this calculation called chi-square. And the way we're going to do this is we're going to see what's the difference between this group and this group and this group. What's the difference in each one of these boxes? Okay, so the difference in this box, 54 minus 42, observed values minus expected values is 11. And over here, the observed values for this group minus the observed values in my expected tables is that difference. And this is equal to the observed values here minus what I would have expected, and this box is equal to the observed values minus the expected values here, okay, which is this. Okay, so now let me think about this for a second. Why don't I just add up all these differences? And the bigger the difference, if the difference is 0, would be 0 if the expected values and the observed values are the same, meaning that doesn't matter if you smoke or not, right? But now, they come out being 0 anyway when I add them together because they're positive and negative numbers. One of the ways that we got around that before was we squared all these values and then we divided by something to bring them back down into the same realm again. Well, our value for chi-square, this calculation for chi-square, is going to be each cell. We're going to do this 4 times for a 2x2 table like this. Each one of these values is going to be equal to, the observed values minus the expected values. I'm going to take that and square it, okay? And I'm going to divide that whole thing by the expected values to bring it back down into the range, the size of the other calculations. I guess I'll have to add another one of these around here. And I'm going to do that for each one of these cells to get a number. The further this number is from 0, that chi-square value is from 0, the more likely that there is an association, that there is a real difference between the observed values and the expected values. So I'm going to actually go through here and calculate this. Okay, so it's going to be equal to, let's see, observed value minus expected value. Okay, and then we're going to want to square that. I'm gonna go over here and I'll tell you what, I'm just going to leave it like that for now. Okay, and I'm actually going to, I don't even really have to do this, do I? This is the observed values minus expected values, observed value minus expected value for each one of these over here. So now, down here, I'm going to say to myself, okay, so this is going to be equal to this value squared, observed minus expected squared, divided by the expected value. So it's going to be equal to 2.9. So this cell down here is going to be equal to the observed value squared, though it's going to be a positive number now, divided by the expected value, which is 55. And this number is going to be equal to the observed value minus the expected value, which is this number, times itself, divided by the expected value for that cell. And the last one is going to be equal to the observed value times itself, divided by the expected value for that cell. That one's a little bit smaller. And my chi-square value is going to be the summation, the sum of all of these. And it turns out to be 9.48. Now, how do I know whether that 9.48, that difference, that chi-square value, the difference between observed and expected value, how do I know that that's big enough to reject my null hypothesis that there's no association between these two variables? What do you think I need to do now? Can I get an opinion? I'm going to show you anyway, whether you want to know or not. So it doesn't matter if you suggest something. What I'm going to do is I'll bet that there is a table for this. I will bet that there is a probability curve, like our normal distribution, like our t-distribution. I bet you there's a distribution for chi-square. And in fact, here is a chi-square table right here. This table represents the chi-square distribution. And let's see. Well, these are my critical values of chi-square for p is equal to 5%, 5% chance of an alpha error, an alpha of 5%, or a 5% chance of being wrong if I reject the null hypothesis that there's no association between these two variables, right? So let's see. I have to, so it's going to be in this column since that's 5%. If I want to be 99% certain, it would be an alpha's 1%. We use this column. But for now, we're using this column. So now I need to know my degrees of freedom. Anybody remember how we calculate degrees of freedom for chi-square? It's the number of rows minus 1 times the number of columns minus 1. 2 rows minus 1 is 1. 2 columns minus 1 is 1. 1 times 1 is 1. So it's 1 degree of freedom. So our critical value for our chi-square is 3.84, right? So, right. Thank you. Thank you very much, Anna Lucia. Okay, so let's go back here. And what was the value of chi-squared that I calculated? 9.4. My critical value is 3.8. I think it was 3.84. Right, that's my critical value. Right. So, do I reject my null hypothesis? Well, since my statistic is larger than my critical value, I know that there's less than 5% chance of being wrong if I reject the null hypothesis. Okay. So I'm going to do this in using SPSS now. Okay, if I can find my data set again. I don't want that one. I don't want that one. Find the right one. It's an output table. It's not that one. Here we go. Okay, smoking and disease. Okay, so I'm going to go in here. I'm going to say analyze descriptive statistics crosstabs. And remember how I did this. Smoking went into the rows. That's my exposure. Presence of aortic stenosis went to the columns. That's my disease. My cells, I told it to show me my observed values. You know, I'm going to tell it to me percentages by rows also. And how about expected values? So if I click OK and OK again, my output table comes up. And let's see what I got in there. Well, maybe I got to make it come up. Here's my output table. And look, here's my 2x2 table, 54 and 40, 44 and 7. But look, it also gives me my expected values. It does it in a single table instead of two of them. It has the expected values and the observed values right alongside of each other. And this is 57.4% percentage by rows. That's your risk. And 36.4 is your risk for non-smokers and so on and so forth. Well, now let's do our calculation of our statistics. I'm going to go in here and I'm going to say analyze. I'm just going to go back to the same thing. Descriptive statistics crosstabs. I'm going to go to, let's see, I'm going to, I don't know why it's making me do it again. Let's see, smoking status. Oh, I'm sorry, I did the wrong thing. Analyze descriptive statistics crosstabs. Okay, and there it is. I knew I found it. Okay, so I'm just gonna get rid of this just to make it a little. I'm gonna get rid of the expected values to make it a little bit simpler. Let's see. I'm gonna go into statistics. I'm gonna say calculate the chi-square for me, and also calculate risk. Okay, actually risk means risk ratio and odds ratio. I'm gonna click continue and say okay. And SPSS bring up the output window. Let's see what we have now. And look, there's our 9.48. That's the Pearson's chi-square that we calculated and compared to our table for chi-square values. And 1 degree of freedom. And what's the probability that we would be wrong if we rejected the null hypothesis? 0.002, less than 5% chance of being wrong. Okay, so now there's something called continuity connection. If you go back into the videos for the full session on this, you'll see that. I wouldn't worry about that for right now, right? So that's our result for our chi-square. So we reject the null hypothesis that there's no association between smoking and aortic stenosis, and we accept the alternative that there is an association. Well, what about risk? Okay, here's our odds ratio for smoking, 2.363, the same as we calculated when we did it by hand, except SPSS calculated the 95% confidence interval, right? Now, our null hypothesis for odds ratio was if there's no association, it's the odds ratio is equal to 1. And our alternative hypothesis is that the odds ratio is not equal to 1. So in this case, we're 95% sure that the true odds ratio for the entire population is 1.4 to 4.1. So that means we're 95% sure that it's not 1. So we can reject the null hypothesis. And guess what this is? This is what we calculated for, if you remember, our relative risk. It calls it cohort presence of aortic stenosis equals, yes, it terms it that way, but we recognize this because we calculated it before, and that's our relative risk. And of course, our relative risk gives us the same result. The confidence interval we would expect if there's no association for this value to be 1, it came out to be 1.58, and we're 95% sure that the true population is between 1.2 and 2.1. So we're 95% sure that it's not 1. So we reject the null hypothesis that it's 1, meaning that there's no association between smoking and that disease. Okay, so last thing I want to do is analysis of variance. Okay, and remember, the deal with analysis of variance was that we're actually dealing with a situation where we're doing the same thing basically as a t-test, right? We're comparing the means of different groups. In a t-test, we're comparing the means of 2 groups. In analysis of variance, we're comparing the means of more than 2 groups. Okay, so I don't think I want to completely drop out of this. Okay, so let me see if I can't find a suitable data file here quickly. So let me see data. Okay, let's see what's in here. If I have a numerical and a categorical variable here, I can use. Let's see what I got here. I don't see any numerical data. Okay, I want to use that one. Okay, how about high school female athletes? Try that one. I hope I'm not using one in the test. I mean, you'll warn me if I am, right? Is this one I used in the test? Did I use this in the test? Nobody's going to let me know? Okay, I don't think so either. Okay, so let's see what we have here. Let's look for a numerical variable here in sports. Sports. I need a categorical variable also. Nah, I don't see a good categorical variable. Nah, I'm gonna find something else. Let me find something. I'll tell you what. Let's go back to our handy dandy North Carolina birth data set. I'm confusing myself here. It's getting late. Get confused easily when I'm late. But it's late. Okay, we're happy with this. No problem. I know. Keep telling me. Okay. Just so you know, SPSS lets you continue to use it for 30 days past your expiration date, kind of like grace period, give you a chance to renew it. Okay, let's see. Let's say that I want to see rigorous mother, marital status, only 2 variables there, drinking status, premature ethnicity of the mother. Okay, let's go back. Let's go here to the variable view. The ethnicity of the mother. Let me find it. Ethnicity of mother, okay, has how many values does that have? Well, in this case, it's non-Hispanic white, non-Hispanic black, Hispanic, and other. Okay, that just happens to be the way that this particular set is, this particular variable is structured. It has 4 possible values. So perhaps I am interested in comparing the mean age at birth, the mean age of the mother that gave birth in North Carolina during this period of time, the mean age of the mother for non-Hispanic white women, non-Hispanic black women, Hispanic women, and all other groups combined. Okay, so that's 4 groups. If I'm going to use the t-test, I'd have to first compare non-Hispanic white to non-Hispanic black, non-Hispanic white to Hispanic, non-Hispanic white to all the others, non-Hispanic black to non-Hispanic to Hispanic, and so on and so forth. I'd have to do this like 5 times, right? So we're going to do this using analysis of variance instead. Okay, so I'm going to say analyze. Compare means. I'm comparing means. Just happens to be it's more than 2 groups. So I'm going to go down here to one-way analysis of variance. Okay, if you watch the videos that I put together, including the one with the pretty flowers at the Brooklyn Botanical Garden, the cherry blossoms, I think it'll help you kind of interpret what you're doing here. But we're looking at the variability and seeing whether the variability between the groups and the variability of the means of each group, if the means of each group are far enough apart and there's little enough variability within the groups that we can predict that that these populations are really different. So my dependent, what is my dependent going to be? What's going to be that numerical variable, which is going to be the age of the mother, right? I'm interested in the mean age of the mother for these different groups. And what is our factor? Our factor is what we're going to break it up into. We're going to break it up into these 4 ethnicities, right? So I'm going to go ahead and do my calculation for analysis of variance. I'll click OK. SPSS. There's a video on, in the class session where I do this. You do this manually in Excel to show you how it's actually worked out. But for our purpose, I'm just going to go down here for now and say, okay, analysis of variance. Well, let's see. There's 4 groups, right? And there's calculated the variability, the mean squares between the variability between the groups, within the groups, and so on and so forth. As it turns out, the F score, the F statistics, the analysis of variance statistics comes out to be 23.5. It's really this mean squared, this really 809 divided by 34. That's where this comes from. And you look at that exercise in Excel, you'll see where this whole calculation comes from. So it's 23.59. So our null hypothesis is that there's no association. The null hypothesis is that the means of all of these groups are equal. The mean age for Hispanic mothers is equal to the mean age for non-Hispanic, is equal to the mean age for white, is equal to the mean age for all the other groups combined, right? An alternative hypothesis is that that not all of the means are the same, that at least 2 of the means are different from one another. Doesn't mean our alternative hypothesis is not that all of the means are different, but at least 2 of the means are different. Okay, so our null hypothesis, they're all equal. The alternative hypothesis is that at least 2 of the means are different from one another. Okay, or that they're not all equal. So I'm going to actually perform this analysis. Analyze. Descriptive statistics analysis variance. I get F is equal to 23.5. Now we can go to a table for analysis of variance. And we look up like the degrees of freedom for between the groups, degrees of freedom within the groups, and we can look up what the critical value of F has to be. In fact, SPSS does that for us, and it tells us that the probability that we would be wrong if we reject the null hypothesis, that all of these are equal, all the means are equal, if we reject that null hypothesis, the probability that we'd be wrong is less than 5%. It's really less than 0.001. SPSS just puts 0 there, but you can interpret it as less than 0.001. Okay, so I'm pretty sure that the means are different, but now we know at least 2 of the means are different, but we don't know which ones. Maybe they're all different, statistically different. Maybe they're not all statistically different. So in order to determine that, we have to do a test after we've determined that we can reject the null hypothesis that they're all the same. We do a test after the fact of that being determined, called post hoc. In Latin, that's what post hoc means, was after the fact. So I'm going to go to analyze. I'm going to go back to compare means, one-way analysis of variance, and now I'm going to go into post hoc. And I think that for the most part, you'll see most people using either Bonferroni or Tukey. I'm going to stick with Bonferroni. I think that's probably what we suggested on the test. I'm sure if I suggested one or the other. These are techniques for actually estimating the probabilities that two of these means, any of these combinations of means, are different from one another. So I'm going to just check that one. I'm going to click OK and continue. I click OK again. Those are different techniques for doing this. They're some are more appropriate in one circumstance, some in others. For our purposes, we're just going to stick with Bonferroni for now. Okay, so let's see. SPSS actually goes through every possible permutation. And it says, let's compare non-Hispanic white to non-Hispanic black. And the probability that the mean for this group is equal to the mean for this group is, 0.000. It's less than 5%. So we can say with 95% certainty, less than 5% chance of being wrong, that the mean for non-Hispanic whites is not equal to the mean of the Hispanic blacks, non-Hispanic blacks. And we can say, well, how about Hispanic? We can say non-Hispanic whites is different than Hispanics. Non-Hispanic white is different than non-Hispanics. Okay, how about the difference between the mean of non-Hispanic whites to others? Well, no, that's not less than 0.001, so I fail to reject that mean. I can't say that means are not equal there. Okay, so Hispanic black, you'll notice it tries every combination. Non-Hispanic black is different than all others, right? That's statistically significant, and so on. And you can just go down here, and others is different than Hispanic as well. You'll see a lot of these are duplicated because Hispanic versus other and other versus Hispanic is really the same result. So what you're doing is you're looking for all the instances. For instance, we cannot say with 95% certainty, less than 5% chance of being wrong, that Hispanic is different than all the other groups combined, right? The mean for Hispanics, mean age for Hispanic women is not different than the mean age for the others as well. So that's how you would interpret this. Okay, so hopefully that helps a little bit with these last couple of topics. Like I said, I'm going to be posting something on logistic regression next week, even though we're officially done with class time. I think it'll be valuable to at least see that demonstrated so that you have a bit of an understanding about it. I really implore you, please go back and like take advantage of any opportunity you have to get those homework grades up so that it'll help you out, like if you've slipped a little bit on homework or something like that. Especially if you guys had like a problem with an exam. If you had an issue with an exam or something like that, and you didn't do as well as you had hoped, you can make up for a lot of that by, making sure you go back and do all the homework. My intention there is that those homeworks are there so you can keep banging away at them until you get them right, so you understand the stuff. They're not there because they're another kind of test. They're there to make sure that you're encouraged to go through them until you can actually get the answers right. Okay, so good night. Good luck on exam 3. We're very close to the end here, and I'm really sorry that that this. I'm sure that this is torture for you to do this in 5 weeks. But at least you have the rest of the summer. For both exercises, you have greater than 80, but you don't need to do the makeup. What I did was for people that I early in the semester, for people that either missed the first exam or and also for people that like really trashed the exam, I gave them the opportunity to take it one more time with the proviso that the most you could get on it would be 80% if you retook it. So if you've got like 80, if you're already above 80, or if you got 79 or something like that, it's not worth doing it again, right? And one person did. One person, I won't, we'll go unnamed here, had like a 93 or a 94 the first time. And then the second time she took it was, got a lower grade. She was concerned I was going to give her the lower grade. So don't take it. I'm going to give her the higher grade. So I'm not going to reduce her grade because the second time she tried it was lower. But that was the point of that, is I didn't want people to feel after that first test that they had no hope in this course, right? Because a lot of you guys you've been away from academics for a long time. First time you take an exam, coming back is a little tough. So take care, guys. Have a good evening, and like I said, I'll be posting again next week. And please post on the discussions boards if you have a lot of further questions. I really want to encourage you to use the discussion board because then we all share the answers as well, rather than just one of you, especially for the exam, because it's only fair if you all see the answers answers or clarifications that I give on the exam. Good night, guys. Bye.